Okay, in this one I'm gonna roleplay as a magician. So as you can see, my current file system is about 900 gigs large. But now if I do ls on this, you will see that I have a 10 terabyte file, which would like consume 10 times more than the capacity of my drive. So how is that even possible? And now even stranger, if I run du on this, so du is for disk usage, on the full file, we see that it's actually on disk only 44K. So how can you create such a file, and why are they useful? That's what that's what we're gonna see in this video, and in which applications they're actually used and so on. So I've created this file by having holes in it, and so basically the way a file is represented on disk is that it has some metadata, and it has basically a table where which points to uh, which part of the file is where on disk. So a file, even if when you read it and write it, it looks continuous, on the actual disk, it can be splitted up in multiple different chunks, which can be all over the place. And that's why in the old hard drives, you had a lot of, you had to defragment your disk sometimes because the hard drives prefer to run, to read stuff and write stuff continuously. On modern drives, well, not modern, but on SSDs, it doesn't matter as much because, yeah, the access time is about the same as far as I understood it. So anyway, you have this table of a chunk of a file which can be at different places. And so what you can do and see, so here this is my little program which I'm going to use to generate this file, is that you can just open the file and use lseek, like so, and we're going to use lseek 64, which is the same thing except the offset is 64-bit to have a very large offset. And what you can do is you can just open the file and seek at a very large place and start writing data. And basically what will be saved on disk is not the whole thing, it's just the data that you saved. And so, yeah, it will allocate, basically, it works by pages, so even if you write like 32 bytes, it will allocate like 4,000 or 8,000 bytes for you. But like the whole, if you seek to place a million, it will not allocate a million bytes for you. So let's see this in action. So let's just do a very large number, which will be, I don't know, 1,000 times 1,000, that's a million, times, I don't know, something else. Let's say 10 this, so this should be 1 terabyte. I think, I'm not sure, let's just play with it. And you do seek cur, so this will set the current position in the file to this. Oh no, it will increment it by this. And let's just have a little buffer where we're gonna put some data. Let me set buff 0, 32, like so, and then let's print I is equal to something in this, and we'll have a little for loop like so. This should be good. Oh yeah, no, it's not good because I need to specify buff. And then let's just very quickly lseek back minus 32, since we wrote 32 and we want to go back so that our file is perfectly 10 terabytes. So if I compile this, remove the foo file that I had an example, and run this executable, you can see that we have this, we should have this thing, but I misspoke. Okay, I just forgot to write it. So of course, if you don't write any data, well, then you have an empty file, so it's a bit pointless. But as you can see now, I've adapted it, and so now it works. So I've also changed the size, well, the logical size, it's called, to 5 terabyte to show you that it works. And yeah, now we have this 5 terabyte files on my 1 terabyte system, but actually it's much smaller than this. So now I will show you how we can actually find these holes in files, because of course, if you have an application that works with a reading files and, I don't know, doing stuff on them, like copying them and so on, you don't want to actually copy these holes, which would actually make your file 10 terabyte in real life. So let me show you this. So I have this other little program which is called list holes, where I just open the file, I have an offset, and we're gonna keep using lseek, and there is other seek flags to find holes and find data in files. So in this case, I start at offset 0, and I'm gonna say seek the first hole after this offset, and so it's gonna return me a different offset, a -1 if there is an error. And then we can print hole found at something something. And we're gonna run this on the file foo, and we see that we found a hole at index 0 because there is one. So now let me keep going and find some data in the file. Okay, and there is this other seek data flag which will seek yeah, the first page that has data on it. So in our case, yeah, we start from the current offset, and then we get the offset where there is the first bit of data, and then we print it. We say we found some data at something, and then we can see that it works, and that yeah, we go from 0 to this to this to this, and so these are all the places where there is holes and where there is data in our file, and you can see it kind of matches what we wrote in our little main. Okay, so I modified the main a tiny bit just to read the 32-bit bytes that we write every time and just print them as a string to see if the data is actually there. And we see that if we do this, we actually find our I is equal 1, I is equal 2, I is equal to something, something, something. I think I made a small mistake where apparently it doesn't work on even numbers. I'm not sure why. Okay, I think it's just due to the fact that I was adding by 5 and not by 2, and it was an odd number, and I don't know, my program is just a small example program, let's not ask too much of it. But basically now I have this 2 terabyte file, and if I list the holes on it, we can see that we have all of our data on there. I'm sure you can find some very something smarter to, if you actually use this in your application. But anyway, that was just to showcase that here is the holes, we can find them, we can find the data, we can yeah, we can find we can read the data from them, and so on and so on. So I wanted to also show a little real life example where when you download a torrent file, if you probably know this already, but the way the torrenting protocol works is that you have multiple peers that have the file, and they give you bits of the file here and there, and the torrenting client just picks up these little parts and just pieces them up together in one file. And to optimize this, so here I have an example. Unfortunately, I cannot zoom in the interface, but this is just a qubit torrent, and I'm downloading an Arch Linux ISO, which is I think a bit less than a gigabyte. And you can see that the progress, well, you can't see because the theme is shit, but it's basically at 4% progress, and it has downloaded little bits of the file. And so it should be like, I don't know, a few megs or something. But if you actually do the disk usage of the file, we can see that, yeah, it's indeed a few megs. But if you list it, so just ls, like so, we can see that it's 1.5 gigabyte. So that's a real life use case of file holes where the qubit torrent has basically it has created the file, it has done an lseek toward the very end to basically pre-allocate the whole size of the file and make sure that the file system understands that this will be in one contiguous chunk. And then as data comes in, it will fill data in, and it will, at the end, it will have no holes in the file. But of course, yeah, it's just to pre-allocate the size and make it easier if you're using hard drives, which you usually are when you're torrenting stuff. So anyway, I know apparently this is used also in virtual machines where when you have like your whole I don't know, your whole file system, the virtual file system, is actually kind of pre-allocated to, I don't know, 100 gigs, but it's actually a big hole, and then as soon as you write a file, or as soon as you write a file, copy a file or something, it allocates the data as needed. So yeah, I hope this was useful, and yeah, I'll see you in the next one.